So today we are going to discuss about chemical potential, and we'll start the discussion in a way so that first we'll try to understand what is different kind of equilibrium related to materials and related to thermodynamics. Then we want to understand that how they are related to the chemical potential if it is in chemical equilibrium. Then slowly today lecture we will understand what chemical potential is and what is its futuristic behavior and how it is very significant in order to understand chemical reaction as well as phase transformation and as well as phase stability and other things. So today our lecture will be on chemical potential. So for that, first we have to understand what are the different kind of equilibrium, because this is very important. So there are two kind of equilibrium you can think of. One is material equilibrium. What it is? If you are talking about material equilibrium, you are talking about number of moles of each substance. Whatever substance are present in the closed system are remain constant with respect to time duration. Again, I am repeating. Material equilibrium, it actually tells you that number of moles of each substance, whatever the substance you are closed system remains constant with time. Now, this material equilibrium having two types of equilibrium. One is reaction equilibrium, another is phase equilibrium. What does mean by reaction equilibrium? When the equilibrium exists with respect to conversion of set of chemical pieces to another. You can tell that the fraction of reactant and products remains constant with the time, but it is a dynamic equilibrium. You should remember, already we understood in our +2 level that rate of forward reaction is equal to rate of backward reaction. Then we are going to reach in the reaction equilibrium. So it is a dynamic equilibrium. Even phase equilibrium also dynamic equilibrium. So what is phase equilibrium? Now, it actually indicates that mainly the reaction equilibrium is really dynamic equilibrium, and if you are talking about phase equilibrium, that phase equilibrium actually represents the fraction of various phase remains constant with time or with time duration. So equilibrium with respect to transport of matter between phases of a particular system, then you can tell that it is a phase equilibrium, and that is very important. We always come across in different metallurgical process, metallurgical heat treatment, and metallurgical phenomena. So this is an important topic in order to understand materials behavior, because in materials behavior, if you can tune them, you can tune the phase transformation process, you can tune the properties end of the day. And that's why structure property correlation concept can come, and structure is directly related to different phases because different phases has different crystal structure. Now we are going to understand about thermodynamic equilibrium. What are the different thermodynamic equilibrium? You can say one is thermal equilibrium, another is mechanical equilibrium, and another is chemical equilibrium. So if you are talking about thermal equilibrium, what it actually tells you? It tells you that there is no change in temperature across the boundary. And if you are talking about mechanical equilibrium, there is no change in potential energy. And if you are talking about chemical equilibrium, and you are talking about chemical equilibrium, then things are different. Because if you are really want to understand what is equilibrium, it actually talks about the state where no gradient of certain parameter, certain potential parameter. So if you want to understand different types of equilibrium, then you have to identify which parameter gradient is important to that corresponding equilibrium phenomena. So now if you see in the picture, there we are talking about, or we are representing, a mechanical equilibrium of a rectangular block. So what it is the important part with respect to become one rectangular block or one body or any physical object to be stable, that its center of gravity should be very much near to the ground, so that, and it will be there in a proper location. So if we start considering the mechanical equilibrium of a block, and this is to get a first field, additional concept we'll understand later, that if it is in the C1 state, the center of gravity is higher if you see in the C3 state. So which one will be the more stable structure? C3. And if you plot that kind of phenomena in the graph, where you see the different configuration, coordinates of the position and different configuration, and the potential energy. And potential energy, basically here we are taking the function of height of center of gravity. So lowest center of gravity of the all the possible state is stable state, which is C3 configuration, and C2 is the most unstable condition, because the central gravity is in the scenario where it is in the height is more, and as well as it is in the not in the proper location. And then also center of gravity, if you see C1, it is metastable, because lowest center of gravity height is not there, it is greater height, but still it can stable for few minutes if you are not part of that particular block. And another things, if you on a plane, that is also named as another different kind of equilibrium, that is neutral equilibrium. That we'll discuss later. But here our concentration on the understanding the mechanical equilibrium. Then what we will do, we will try to correlate this kind of mechanical equilibrium with the concept of chemical potential. Okay. Now, if you see, if you want to correlate the potential energy and the chemical potential, then you have to understand how chemical potential will be varied if you want to look at the particular system. Suppose we can better understand the chemical potential by looking at particular system with a difference in potential energy. Suppose we just understand that with respect to potential energy, which is a function of center of height of the center of gravity, that is going to tell you about the mechanical equilibrium. Now we try to correlate with the chemical potential, or try to not correlate, we try to get the analogy of that. So we can better understand the chemical potential by seeing at a system with a difference in potential energy, or you can tell a gradient of potential energy. So we can take a simplest example slide. They may exchange particles. That is the assumption. We are first taking certain assumption that so that we can understand the scenario. But the two systems are not yet in diffusive state. They can exchange particle, but they are not at the diffusive state. Now what we will do, we assume that okay, we can start from mu b, which is greater than mu a, so that particles will flow from B to A. Since just take a concept that if mu is greater, then from that the particle will flow, and mu is a chemical potential. And now the difference in chemical potential, if you measure del mu is equal to mu b minus mu a, you can represent easily. Now we can introduce now a difference in potential energy between the two systems. Take an example. If you take example for charged particles, we may introduce an electric field with a voltage of del of capital V, and we apply this kind of charge thing to all particles in the system A, so that rise or we can raise their potential energy of del mu. So what will be the difference of the potential difference? How you can represent the Q into del of capital V equal to Q into VB minus VA, that is del mu. So this kind of analogy you can also find by using difference in gravitational potential, that can be MGH, mass, gravitational acceleration and height, or other ways to introduce a potential difference. So here we are taking the example of voltage difference. So now we can reanalyze the system if it is required thermodynamically. We are going to reanalyze the system thermodynamically. We have changed the potential energy of all particles in system A, but we have not made any changes in system B. Now what we have done, we have changed the potential energy of all the particles in the system A, but we have not made any changes in the system B. This means that actually what it indicates, it means that we have changed the energy of a system A, and Helmholtz free energy if you are talking about A or Fa, but we have not changed their UB and UFB. Means we are changing the energy of system A, we are changing Helmholtz free energy of the system A, but we are not changing the Helmholtz free energy or as well as the energy of system B. Hope all of you understood that. The change in free system A is by the change in internal energy, and this means that Avogadro number multiplied by Q into del V. Q is a charge. This means that the energy of every state in a system is changed to del of M into U, and that is equal to Q into del of capital V. This means that the chemical in a particular system A in the state, a potential what you are applied, if you are talking about state 2 and state 1, then this means that chemical potential in state system of A in state 2 after the potential is applied, that is the voltage potential, can be expressed what I have written in the slide. And what it is written, that mu A of state 2 equals to mu A of state 1 plus del mu, the change in that potential. Now mu A of state 1 equals to, if we replace del mu by mu B of state 1 minus mu A of state 1, then what you are getting, that mu A of state 1 and mu A of state 1 having one positive or negative sign, that will be cancelled out. So you are going to get mu B of state 1. And initially we told that mu B has the potential in the system A, B, we are not going to change. We have not changed either UB or Helmholtz free energy for the system B. So now what will be the mu B of state 1 is equal to mu B of state 2. It's a very important statement. It is telling that the difference in chemical potential, please pay attention, the difference in chemical potential between two systems A and B corresponds to potential energy difference needed in order to establish diffusional equilibrium. So the chemical potential, difference in chemical potential to system A and B corresponding to certain potential energy difference is actually required if you want to establish diffusional equilibrium. Then another concept, here the mechanical equilibrium slowly reaching to a diffusional equilibrium concept, and then we can tell that we can use this concept, we can measure the chemical potential and we can apply potential difference and we can determine what potential difference net particle flow will stop. when net particle flow stops, that is the equilibrium, diffusional equilibrium. Now we are going to next slide. So in general, what we have seen, if two systems have same temperature, there is no net energy flow, heat energy here I am talking about. If system have same pressure, no net change of volumes. That two thing is visually analyzed. But if two systems have the same X, there is no net flow of particles. What is that X? Just previous discussion, few minutes ago, we can identify the X. X is chemical potential. Actually, the potential, and it is related to the potential energy gradient. So this is a change in potential. If it is zero, if the two systems have the same chemical potential, there is no net flow of particles. That is diffusional equilibrium you can reach. So now just go through certain relevant thermodynamic potential determining the stability of the system. In terms of, if you say that pressure difference drives volume change, that we already we should keep in our mind. These are, you can tell, summarize of all the previous lectures, what I understood. And the temperature difference drives to entropy change, and chemical potential difference drives to mass transfer. Means chemical potential, there is a deviation that actually leads to mass transfer. And the relevant thermodynamic potential which characterizes the stability of the system is dependent on the state variable, which are held. If you travel, constant entropy, constant temperature, how it goes to constant V, internal energy is going to be constant. Then Helmholtz free energy concept you can come into play for constant V. Constant P, the enthalpy as well as the Gibbs free energy concept will come to play. And these are the relationship already we have come across from previous lectures. The most conditions are one of the constant P and constant T. So hence G, Gibbs free energy, is the most relevant thermodynamic potential. However, we should remember that depending on the state variable being held constant, any one of the four potential could be relevant potential. Depending upon which state variable you are taking constant. Sometimes you are taking constant entropy, sometimes constant volume, constant pressure. So based on that, you have to understand which potential will be more relevant, which thermodynamic potential will be more relevant with respect to understanding the stability of the system. It's a very important understanding or concept. Now we are going to discuss more detail in the differential form and incremental differential form of addition of second element to a first element, how it is related to the chemical potential. So it is very important. It is really interesting to know how the free energy of a given phase will change when atoms are added or removed in case of alloys. What is alloy? When two or more metals are come together, they mix properly and then create a new metallic structure system, and mixing after the not mixing the proper solution, then you are going to get the metallic alloy, and it is a homogeneous composition throughout the system. If it is there, then you can tell that single phase alloy system. So it is very important in case of alloy. It is of really interesting to know how the free energy of a given phase will change when atoms are added or removed. Suppose you are taking a very small quantity of A, that is DNA mole, is added to a large amount of phase at a constant temperature and pressure. And the size of the system, then it will increase by DNA, very incremental increase, a very small increment. And therefore, the total free energy of the system will also increase by a small amount, that is D capital G dot. Why I am taking G dot? Because I am trying to represent in a complex system. And generally only G, it is related to the molar free energy kind of concept. So that's why I want to differentiate it. Say I am putting simply G dot. And if DNA is small enough, G dot will be proportional to the amount of A added. It's very simple. What is free energy? Free energy is the available energy of a system to do some work. Now you are adding certain things incrementally, small quantity of A, then the free energy of A will be enhanced with respect to the system, and overall free energy of the system will be enhanced. So how it will enhance? It is directly proportional to the amount of A added. So now we can write what we have written in the slide, that dG capital G dot equal to mu A into dNA, and we are taking for that TPNB constant. That the proportionality constant of mu is called the partial molar free energy of A. Or you can alternatively can tell that this is the chemical potential of A in the phase. So mu A depends on the composition of the phase. Now we are understanding that, okay, the proportionality constant is mu A. You can tell is partial molar free energy, or you can tell it chemical potential. Fine. But how the chemical potential is depending on the composition, what are the factors are going to govern the chemical potential mu A? So in the phase, mu A depends on the composition of the phase, and therefore DNA must be so small that the composition is not significantly altered. Now please understand that composition should not be significantly altered, so that DNA should be very small. Otherwise, that incremental derivative form, mathematical derivative form cannot be valid, because when you are getting a differential form, you are telling that the denominator part is that quantity tends to limit tends to 0, means it's a very small. So that mathematical concept should have physics-based interpretation in order to represent chemical potential of A. So now, since this scenario is valid for today's discussion, now we can represent mu equal to del G dot del Na T comma P Nb, when T comma P comma Nb, these are the constant, means number of moles of Nb is constant, B is constant, pressure is constant, temperature is constant. And already I told that G dot is used here for gives energy to emphasize the fact that it refers the whole system. Actually, generally we used to use the G will be used to denote the molar free energy, and that is actually when you are talking about molar free energy, capital G is actually independent of the size of the system. But here, when we are talking about G dot, it is not that case. That's why I put G dot to differentiate. This is to emphasize the fact it is representing the whole system. So dG dot equals to mu A into DNA and mu B into DNB. This equation can be extended by adding further terms of solution content more than 2 components. And if you want, you can vary temperature and pressure, because first concept, what you have done, you go for binary and you are telling that no variation in temperature and pressure. Now you are taking that also, okay, we are going to vary the temperature and pressure, and we are going for multiple component system. There you can write that dG dot equal to minus SDT plus VDP, mu A DNA, mu B DNB, mu C DNC, in any n number. The number of multi-component will be the factor. You can decide how many terms you are now going to include for this kind of expression. If 1 mole of original phase, now come into scenario, now we have to understand how these expressions are going to a scenario where you can correlate the chemical potential with the mole fraction of that particular element. So suppose you are taking 1 mole of the original phase contain XA mole of A and XB mole of B, and the size of the system, then what you can tell that it will increase without altering the composition of A and B. Now in this way, easily you can understand that G, now it will be related to a scenario where G is equal to mu A into XA and mu B into XB. From there, if you understand, then you can get the previous expression. Already we have discussed that G, how it is related to the particular phase G alpha equal to XA GA XB GB, then RT in the bracket XA ln XA plus XB ln XB, that equation. And if you combine with the newly what we discussed, that equation mu A and XB and mu XB, mu A XA plus mu B XB, then we will directly get mu A equals to GA plus RT ln XA and mu B equal to GB plus RT ln XB. That you can get the expression in the scenario. That now if you use this equation and the previously and the unit of this partial molar, not partial, molar free energy is J per joule per mole. So now we understood that there is this good relationship between particular chemical potential and corresponding Gibbs free energy as well as temperature and the mole fraction of that particular element in a alloy. So that part is over. So now we can understand the question, answer the question of that how the free energy of a given phase will change when adding in case of alloys. That answer we can got, that how free energy is changed. It is actually through the representation of chemical potential we can understand the concept. Now we have to go through this plot. What is the plot? This kind of plot we have went through, we have gone through a lot of times few class ago. So here is the chemical potential actually indicate the activity. So what it is telling, the more the chemical potential, things are more active, material are becoming more active. So if you see, suppose there is a plot called G alpha. This green curve, that green curve what you are seeing, it actually representing green of alpha phase. And alpha phase, both A and B component can be present. It's not like that only A or B, because it is in the is a pure side A, and the one side is pure A and another is pure B. In between, whatever the things are, there is a composition change. So there is a both element will present. Now we have to find out for a particular composition what will be the chemical potential of that particular element. So please remember, chemical potential cannot be denoted for a particular phase. Chemical potential always of a particular element present in a particular phase. Now onwards, nobody should forget that statement. Gibbs free energy can be assigned to a particular phase, but chemical potential cannot be assigned to a particular phase. It can be assigned to a particular element present in a particular phase. Okay, so how to do that? So from the, suppose first we will go for X2 composition. X1 is there, we are going for X2 composition first. So X2 composition, what will happen? You just draw a tangent to the curve. And when this is the X2 composition, at that composition, and since you are writing only 2D diagram, free energy versus composition diagram means you are taking particular one temperature constant. That's why you have drawn in a 2D, two-dimensional form. Otherwise, you have to take another axis where temperature will be a variable. So since you are taking a particular temperature, that's why you can draw in a paper in a 2D diagram form, schematic diagram. So in that schematic diagram, this point is corresponds to X2 composition, means mole fraction of B. If you take X, then X2 mole fraction of B, that particular composition, you are getting this point. Now you have to draw a tangent, and that tangent cut pure A line and pure B line. And when it cuts pure A line, that point actually represents mu A of mu A, chemical potential of A in alpha phase, mu A alpha. Suffix always tells the element, and prefix and the top of the superscript. Subscript always tells the element, and superscript always tells the phase. This is the usual convention. You can tell that it is a convention. If you compare that mu A in alpha is much less than mu B in alpha. So at that particular composition, at that composition and that temperature, whatever the temperature you have taken for constant, that's why you are able to draw the figure in a particular 2D fashion. So that particular composition and that particular temperature, you are seeing that mu B alpha means mu B in alpha phase is much greater than mu A alpha phase. What does means? Means B is more active. B atoms are more active in alpha phase compared to A atoms at that particular composition and particular temperature. Now, if you go for same thing, just you change to the composition, X1 composition. Now you are seeing that things are totally reversed. Now mu A in alpha is much greater than mu B in alpha. So here B atoms are more active. So when you go this side, when you go X1 composition at X1 composition and at particular temperature, the scenario is like that. A atoms are more active in alpha phase compared to B atoms. So this is the concept associated with this schematic diagram. Now we have to take a particular example of magnesium silicon, because that plot, that diagram, that phase diagram and that system tells you a lot of conceptual understanding of such kind of thermodynamic behavior with respect to Gibbs free energy concept. So okay, now we know that magnesium has a HCP structure, hexagonal closed pack structure, and silicon cubic structure. That part we already understood. Now what we have to do here to understand the scenario, suppose there is a two phase, one is alpha silicon phase, one is alpha magnesium phase, and for that alpha magnesium phase, this one is the, you can see in the plot that just alpha magnesium is written to close to one curve, that is representing the alpha magnesium Gibbs free energy, another is representing alpha silicon Gibbs free energy. And this, from this plot, we will try to understand how the equilibrium, chemical equilibrium or diffusional equilibrium are going to attain, and what is the scenario at that position. Now first, same way, just like previous slide, you take a composition which is touching the G of alpha silicon free energy diagram, just like previously, and you are to find what will be the activity. Mu silicon as alpha silicon, you will get much greater than mu of magnesium in alpha silicon. So you are going to get the activity. So when such kind of scenario going to happen, if you check that, if you welded 80% of silicon and 20% of magnesium, and what is the scenario? Then you're going to get that if you get the such a kind of scenario, then what is happening? You are going to get higher activity of silicon. Okay, because in this case silicon is more, and that part also seen from the chemical potential, how the tangent is cutting the pure silicon axis and pure magnesium axis or line. Now you go for same thing alpha magnesium. In alpha magnesium, you are seeing that the higher activity is the magnesium, because their mu of magnesium in alpha magnesium is much higher compared to mu of silicon at alpha magnesium. Alpha magnesium is a phase, so at alpha magnesium, so that is the higher. Now these two phases we are now discussing, when these two phases become or coming to a state when they are in equilibrium to each other. This is phase equilibrium, and I told that this is under the materials equilibrium. And then we have to understand how it is related to. So for that, what we need, since here if you see, if the mu silicon in alpha silicon and alpha silicon phase, then the activity or the chemical potential should be in decreased, and in alpha magnesium phase, the chemical potential of magnesium should be decreased. How it will decrease? Only by diffusion. The silicon will move to magnesium side, alpha magnesium, and magnesium is moved from silicon side. So when this kind of movement in the chemical potential slowly decrease, and then come into scenario when there will be a common tangent. If you see the green star, these 2 points, and if you draw a tangent, the minimum point of both of those gives energy of that both phase, then you get a common tangent, and in that common tangent, if you see the mu silicon in alpha silicon phase and mu silicon in alpha magnesium phase are equal, and mu silicon in mu magnesium in alpha magnesium phase is equal to mu magnesium at alpha silicon phase. So there is the chemical equilibrium. So common tangent from that two phase equilibrium you can see, and that's way you can understand how chemical potential is important to get or define, or in order to reach the equilibrium state of between two phases, since it is a binary component. Now we have a groundwork regarding understanding of the chemical potential. Now what we will do, we will try to revisit the definition of the chemical potential from the understanding base what we reached today class. So till date, when we are not talking about transferring mass across the boundary, we are not talking about that kind of mass transfer across the boundary of a system. We used to talk about always closed system. But when we are talking about chemical potential concept, then we are actually telling that there is a mass transfer can possible, and after certain time when there will be no gradient of chemical potential, there will be equilibrium with respect to diffusion, or the diffusional equilibrium or chemical equilibrium. So there will be no mass transfer. So now system characteristics is changing. We are now talking about open system where mass transfers as well as energy transfers are allowed. So a homogeneous open system, if it is a consists of a single phase, and what is written in the slide, and allows mass transfer across its boundaries, a homogeneous open system, we are taking a single phase and which actually allows the mass transfer across its boundaries. The thermodynamic functions depend not only on temperature and pressure, but also is variable necessary to describe the size of the system and its composition. Now it's a very important statement. Now we are talking about composition, the importance of the composition with respect to understanding or determining or evaluating thermodynamic functions. The Gibbs free energy of the system is therefore a function of temperature, pressure, and the number of moles of the chemical potential. And so if you see the Gibbs free energy, dg equal to del G by del T, del G by del T at constant pressure Ni dt, and this is the exact differential of G, and you can written in the such expression del G by del T at constant pressure and Ni constant number of I component into dt, and del G by del P at constant T and Ni into dP, and del G del Ni Tp and constant Nj not equal to, other than I component all are constant, then dni. So these partial derivatives of G with respect to temperature and pressure respectively, we can recall the concept of entropy and volume. And that partial derivatives of G with respect to Ni, or that Ni for a particular element, the number of moles or whatever, is the chemical potential of the component. That can be written as mu I. You can see here the partial derivative of G with respect to temperature and pressure respectively. We can tell that the partial derivative of G with respect to Ni is the chemical potential of the component I, that is mu I. I always told that you cannot assign chemical potential to a phase, only you can assign chemical potential of a component present in particular system. So mu I equal to del G del Ni at constant temperature pressure, and where n J not equal to I means I other than I, all the component of that system are not going to vary in the number of mole fraction or any number of atoms. So for open system, now the relationship are changing till when it's closed system and the open system, the difference is you mu oriented term you have to add, that is summation of I mu I dni. That term you have to add with the usual closed system representation of internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. Now the definition of chemical potential with respect to all the thermodynamic potential functions are given here. That is del G del Ni, where T, P, and N, J less not equal to I, means other than I component or all the component of the system should be constant. And same way you can see the for the Helmholtz free energy correlation with the chemical potential and Helmholtz free energy, chemical potential, enthalpy, and chemical potential with the internal energy. Now we understood what is the actually the chemical potential means, what chemical potential represents. Now we have to understand the condition for equilibrium for a heterogeneous system. Equilibrium condition of the closed system, if we recall, at constant temperature and pressure, what is that? dG at constant temperature and pressure, Ni, if all the components are constant, number of atoms for the any component, then it is equals to 0. But for such a system which allows transfer, if you are going for understanding a system where you are allowing the transfer of both heat and mass, it is open system. Suppose you are taking open system. Then if you are talking about open system, then you are allowing transfer of both heat and mass across the boundary of the system. Then the scenario is totally different. You have to take care of then what is the chemical potential concept. The chemical potential of each species then must be the same in all phases present in the equilibrium. So you have to take another thing, mu I alpha equal to mu I beta, mu I gamma equals to mu I delta in this way. Here alpha, beta, delta are denoting the different phases in the system, and I is denoting the different component of the system, what we understood the previous slide lecture also. Then partial molar properties, if you want to now the concept is coming scenario where you have to understand the partial molar quantities or properties in an open system. Now we are talking about open system because we are considering that mass transfer and heat transfer will be possible across the boundary. So we are talking about open system. So in open system consisting of several components, the thermodynamic properties of each component always depend on the overall composition. And not only overall composition, you have to also think about, in addition to that, temperature and pressure. So till now what we understand that for open system, several components of thermodynamic properties, in addition to temperature and pressure, we have to also consider the overall composition. So chemical thermodynamics of such kind of really relies, you have to understand that, relies on the partial molar properties of the components. So now we have to find out what are the partial molar properties. The partial molar Gibbs free energy at constant pressure, temperature, and other element Nj is constant, then you will find that different partial molar enthalpy, entropy, and volume. You can write very simple way. Hi, and the convention to write that Hi bar, you have to give one bar in the head of that Hi, and del H del Ni at constant temperature, pressure, and Nj not equal to I. Already we understood what does mean by Nj not equal to I. And same way Si and Vi you can represent. This is very important concept. And also you have to take a note that the partial molar derivative may also be taken under condition, under constant pressure and temperature. It can be, that derivative may also be taken under condition that you can also represent with respect to constant pressure and temperature. So these are the really important understanding. Now we are going to learn about Gibbs dual-Duhem equation, what it is, why it is required at all. So for that, we have to understand certain important thing. In absence of non-PV work, you are not going to consider here non-PV work. So extensive property like Gibbs free energy of a system is very important. It's becoming important. What we are seeing that for in the absence of non-PV work, extensive property, we know what is extensive property, and such as Gibbs free energy of a system can be represented by a function of partial derivatives, and that gives to an equation. They actually represented Gibbs free energy for such extensive property when they are looking at a system which are not going for any PV work, a non-PV work. So in the absence of non-PV work, they used to get such kind of things. And to be function of partial derivative, if you see, G equals to summation of Ni for I component del G del Ni at constant temperature, pressure, and Nj not equal to I. And the context of G itself is often you can refer as a integral Gibbs free energy. For binary system, you can write G equals to Na mu A plus Nb mu B. And if you differentiate this equation, G equals to Na mu A plus Nb mu B, you will get dg equal to Na d mu A, dna mu A, and Nb d mu B, and dnb and mu B. And if you use that concept of at constant temperature, pressure, G is also can be given by dg equal to mu A dna and mu B in dnb, then you directly can show that Na d mu A and Nb d mu B equals to 0. And that is actually gives to an equation for binary system for a constant temperature and pressure. So that I component Ni d mu I equals to 0. So for any arbitrary system, if you want to write the Gibbs equation, you can write like that. You can write that S dt minus V dp plus summation of I Ni d mu I equals to 0. This is actually the equation of Gibbs duhem given by Gibbs duhem, and that is very important equation to understand the possibilities of how extensive property like Gibbs free energy is varying for different system like open system. And then you can write all the corollary expression for the open system to represent the Gibbs duhem equation. So today class is over. Thank you so much.